You have a superpower. You already realize that being able to code gives you the ability to create things with just your mind and your fingers. I see programming as a way of learning mathematics. Writing programs and running them on data is a learning modality. Your ability to create vectors and matrices will enable you to build stuff with them and do fun things. Through coding, we escape two pitfalls of the traditional linear algebra course. Some linear algebra courses are a bit too abstract for many of us. This makes the concepts hard to grasp and keeps us at a remove from the applications. Some linear algebra courses are too tedious. They require a lot of hand calculation, possibly with the aid of a calculator. Some hand calculation is useful to help acquaint you with the operations, but it should not be considered the only way of learning a procedure. My hope is that by coding computational methods in linear algebra, you'll better learn both the methods and the way they apply to real problems and real data. The example problems I use in this course have a computer science flavor to them. That's because I'm a computer scientist, and I expect many of you have some background in computer science. I developed this course because I felt too many students of computer science were going off and learning linear algebra and coming back and saying, well, that's nice, but what does it have to do with what I'm interested in? By drawing on your ability to program, I hope to give you an introduction to linear algebra that plays to your strengths, gives you the power to build things that are fun and interesting, that makes linear algebra come alive for you, that puts in your hands the tools to use linear algebra in the problems and applications that are interesting to you. Programming is the power to create, and creation has a two-way relationship with understanding. My twofold hope then is that the creating you do in meeting the challenges of this course will help you to reach greater understanding of the material. And two, that greater understanding will give you the ability to create even more. In addition, I want to highlight three specific concepts from programming that are relevant to this course: data abstraction, procedure abstraction, and what I would call procedural sophistication. First, data abstraction. In the language of object-oriented programming, you can have several classes that implement a single interface. A client of that interface need not know the details of the class used to implement that interface. In linear algebra, data abstraction gives us the concept of a field. Think of a field as a class that implements the operations plus, minus, times, and divide. As long as a class's implementation of these operations satisfies certain algebraic rules, we can use it to do linear algebra. Being able to slot in any field gives linear algebra greater generality and therefore greater applicability. For example, the field of real numbers can be used in doing computer graphics or computer vision. The field consisting just of 0 and 1 can be used for applications like cryptography. And the field of complex numbers comes up in signal processing and in analyzing dynamic processes that unfold over time. At the beginning of this course, we informally describe the field, and we use it throughout the course. I will say, though, it's a somewhat leaky abstraction. Towards the end of the course, we have to get more from our field, so that field that consists just of 0 and 1 has to be put aside for that part of the course. The field consisting of the complex numbers is crucial for some of the advanced topics in linear algebra. Unfortunately, we won't get to some of those topics in this version of the course. More on that topic later. There's a lot to learn here, but it boils down to learning certain kinds of addition and multiplication operations. In this part of the course, in order to better learn these operations, you'll implement your own vectors and matrices. You won't have to do this from scratch. Since you'll be working from a template, all you have to do is fill in the implementations of these operations. Second, procedural abstraction. Programmers quickly learn to work with APIs, application programming interfaces. This means they learn what a suite of procedure calls do and how you can use these in combination to get things done. Programmers don't need to know how each of these procedures is implemented. It's enough to know what it accomplishes. In the middle third of this course, there are a lot of concepts swirling around. Coordinate representation, basis, dimension, rank. Each concept on its own is not so hard, but it might be hard to keep them straight to develop an understanding of the relationships between these concepts. To help you develop a feel for the connections between these concepts, you'll write programs that realize the concepts and that build one upon the other. They all ultimately rely, however, on some black boxes, procedures whose implementations we won't study, at least at first. Only once we've gotten through this middle part of the course will we be able to open up the black box and see how it's implemented. In the meantime, however, I expect you to work with this black box without knowing what's inside, just as you would with the procedures of an API. Third, if you've done a fair bit of programming, I expect you've developed what I call procedural sophistication. You're much better than the average person, and quite possibly better than even mathematicians from the pre-computer past, at understanding and coping with complicated procedures. You're not afraid of a bit of complexity. Even if you don't understand a procedure at first, you're able to work through it, try some examples, get to know it, develop a feel for it over time. If you do have this skill, it will help you a lot in the middle third of the course and in the final third. In the middle third of the course, while we're dealing with all these concepts swirling around, you're going to see some fairly complicated mathematical proofs. This sounds intimidating, and with good reason. These proofs are a little difficult to follow. But fundamentally, they're procedural in nature. They're algorithmic proofs. And so, because of your procedural sophistication, you'll be better able to follow them. Understanding these proofs might require you to think harder than you're used to. But it turns out that many of these mathematical proofs are procedures in disguise. Keep that in mind, and maybe they won't turn out to be quite so difficult. To help you along, I'm assigning problems in which you'll write programs that mimic the structure of the proof. To help you in the process of relating proof to procedure, I'll assign some problems in which you write programs that embody the idea of the proof. In the final third of the course, we'll start opening up those black boxes and learning the procedures that are inside. Here, too, your procedural sophistication will help you. We'll code these procedures, and your programming ability will help you develop greater understanding. You are here. At the end of the course, if you're still with us, you'll be here. The first third of the course consists of a lot of mechanics and definitions, working with vectors and matrices. This section of the course introduces more questions than it answers. The fundamental questions and computational problems that are introduced in this part of the course will be addressed throughout the rest of the course. The middle third of the course, the concepts we study will illuminate the topic, enabling us to answer many of the questions that have come up so far. We'll get only a hint at this point, though, of the computational solutions, the procedures that we'll study in the last third of the course. The real solutions to the computational problems come in the final third of the course, where we study what makes the black box, the solver, work. At this point, I must confess, there's a fourth third to the course that I teach my Brown students. The material around here consists of advanced topics that build on everything we've done before. Some of the most interesting applications can only be addressed in that part of the material, including image compression, page rank, dimensionality reduction, and principal components analysis. I very much wanted to teach these advanced parts to you, but 8 weeks was deemed quite long enough for an online course. So instead, I plan to offer an additional course for those who endure this course. So hold on to your code. A word about this diagram. I'll make it available on the course site, but don't try to read it all. It's a map, and just as you wouldn't read all of a roadmap, you won't find it useful looking at this until you've covered some of the territory. It's there to help you keep track of where you are and where we're going.